Okay, good morning and welcome. I'm Carl Lampert. I'm the technical director of SVC, and I'm very happy to be able to introduce our honored guest here, Vivek Subramanian, and he's from the Electrical Engineering and Computer Sciences Department of the University of California, and I spent many years there in the past, and I know it's such a great place. What's interesting is he has the Best Teachers Award, and he also has the Best Paper Award from IEEE, from the Electron Devices Division. So I'm expecting some great stuff out of you. So anyway, we're really happy to have you here. And I will introduce the title, Printed Electronics, Innovations in Materials, Processes, and Devices. It'll be a 40-minute talk. Vivek, please.
Thank you.
Great.
Thank you. It's good morning to all of you. It's a pleasure to be here today. What I'm going to do in this talk that I give you for the next half hour to 40 minutes or so is try to give you some perspective on things that are happening in a field that largely is doing its best to avoid vacuum deposition. In other words, what we've really been focusing on as practitioners in this field is trying to enable solution-based deposition. Now, why is that of interest to you? Well, I'll try to give you different perspectives on it. First, for those of you who are looking at printed electronics and have heard a little bit about it and are saying, how does the state of the art in printed electronics compare to what we can do in vacuum processing? I'll hopefully give you a snapshot of that, identify where we are in terms of sort of our tooling, the materials we work with, the processes we use for fabrication, and then some system applications. Then in addition, what I will try to do is I'll try to show you how there's opportunities along the way for these systems to play together. If you look at what's happening in printed electronics, a lot of the early applications, including some that have become commercial, really leverage the combination of coding techniques coupled with the high-speed, high-throughput patterning that is achieved by print. And then finally, I'll try to tell you where we're going out of this. And actually, in many cases, a lot of the things that we're working on, we've really been learning from the lessons that sort of traditional large area coding has had over the years. And that'll identify some of the shortcomings that we're trying to deal with moving forward. So obviously, I'm in electrical engineering and computer science. I'm a semiconductor guy by training. I started in the semiconductor industry. In fact, I started working in LPCVD and then over the years moved into other things. And what's been really interesting for me working in printed electronics, which is a transition I made now 15 years ago, is how young we are as a field. Because if you look at where we've had success, or what's driven our success, it really has driven a dramatic amount of vertical integration in what we do. So even though I'm in electrical engineering and computer sciences, my students, we build our own printers. We do fundamental studies in fluid mechanics. We develop and synthesize our own materials. So I was the first electrical engineer to ask for fume hoods in electrical engineering. And then we build various types of devices. I'm a transistor person by training, so the majority of what I'm going to show you today is focused on transistor-like devices, so switches. And to begin, first I'm going to give you a snapshot of where we are in print. And this is an area where my group has definitely had a tremendous amount of success. And then I'm going to step back and tell you why we print. So, as far as printing is concerned, if you look at what we're capable of doing, my group works on two main printing techniques. One is inkjet, and the other is gravure. Now, when we started in inkjet 15 years ago, we used to build our own printers. So this represents one of the early printers that we built. But it turns out today I no longer build my own printers. Printing has come far enough along today that, as far as inkjet is concerned, that there are very good commercial tools available, both at the pilot scale, at the lab scale, and indeed at the industrial scale. Now, why do we use inkjet printing? Well, it has certain advantages and disadvantages. The big advantage of inkjet for printed electronics is we can have very pure materials as our input materials. Inkjet works with very low viscosity inks. That's bad when you're trying to build up thick films, but it's good when you want very pure incoming material because your formulation can be the active material that you care about, plus a relatively low viscosity and relatively high evaporation rate solvent, which allows you to deliver very clean final films. Resolution of inkjet has certain problems. While the resolution of inkjet has scaled dramatically, there's a fundamental direct trade-off between inkjet resolution and throughput. Because resolution in inkjet is set by the size of the drop. So all else being equal, as you make your drop smaller to get finer resolution, your throughput goes down. It has additional problems. In particular, when you are trying to do fine lines, when you shoot about 1 million drops out of an inkjet head, they don't all hit the same spot. There's a certain solid angle of variation in where they are placed, and that gets worse as your drops get smaller. So fundamentally, line edge roughness, which is something as in electronics we care quite a bit about, gets worse as you go to finer features. So we did a lot of work on inkjet. I'm not going to spend too much time on it, but now we've largely concluded that it's really good where we want to take advantage of the things that inkjet is good for, which is high-quality thin films with low contamination and the ability to spot deposit certain materials in certain locations. The technique we've largely moved on to for very high resolution is gravure printing. Now, most of you are at least qualitatively familiar with gravure, or at least the products of gravure, because most currency worldwide is printed with gravure. Postage stamps, which nobody really uses anymore, are also printed with gravure. And then posters and glossy magazines are printed with gravure. So in gravure, I'll talk more about gravure in a few minutes. What you have is you have a hard metal cylinder that is inked and then transfers your pattern. Because you are using a rigid master, it turns out you get very good pattern fidelity. Now, traditional gravure, as in use in graphic arts, sits at about 30 to 40 micron resolution. Security gravure, which is used for printing currency and is a very closely held technology, is down in the 6 to 7 micron range. It turns out getting information about the security industry is very difficult for obvious reasons because it enables forgery. So I always tell my students that, things don't work out in research, they have an alternative career path. But it turns out what we've been able to do by sort of treating printing as a science, and this is a key lesson that I'm going to try to give you, and for you all as from sort of coding, you've been treating coding as a science forever. But if you look at printing, a lot of what's happened in the printing industry, a lot of the practitioners of print treat it as an art more than as a science. Now, they do that for two reasons. One is it's a really, really old industry, and so, if you're doing graphic arts, we've hit sort of performance targets more than 40 years ago. And then the other is it allows them to keep the industry relatively closed. So for example, if you want to learn about ink formulation, it's really hard to do that because all the ink formulation companies don't tell you how to formulate inks. And there's not a lot of good papers on how to formulate inks. And that allows these companies that do sort of professional ink formulation to hold it very tightly. But we've been able to address some of that. And by treating printing as a science, we've been able to take techniques that sit at 5 to 10 to 30 micron range and push down to single micron range. And indeed, I'm absolutely positive we'll get down to the sub half micron, so sub 500 nanometer range in terms of pattern quality and so critical dimension, while maintaining really high throughput. So the big advantages of gravure are very high throughput, very good pattern fidelity, and very good scalability. Now, the big question you're probably asking is, why are you printing anyway? You look at these resolution numbers and you say, okay, that's not competitive with fine line lithography, but clearly we're getting in the ballpark where we're getting close to what large area lithography does. So why print? Well, the answer is pretty simple. If you calculate, you sort of build a cost of goods sold analysis model, so you sort of build up an economic model for what you can do with print. It turns out printing is actually not, people say printing is cheap, that's why you print. But it's actually much more subtle and complicated than that. Printing is really good for spitting out large areas of material because the throughputs are really high. I mean, we're printing at 1 meter per second, and frankly, we could go faster. We're limited by our tooling. There's no fundamental reason we couldn't go faster. But we're not delivering the line widths of state-of-the-art lithography, for example. So if you go in and build an economic model for what printing is good for, it's not good for putting lots of functions in a small area. It's actually much more expensive than conventional subtractive processes. So for example, the cost of a silicon transistor on a silicon wafer today is about 1 nanocent. The cost of a silicon transistor on a piece of glass today is on the order of about 0.1 millicents. You calculate the cost of my transistors, and they're about 2 orders of magnitude more expensive than that. So it means that printing is not good for applications you're trying to pack a ton of transistors into a small area. So if you read the popular press, you hear that printing will be great. One day you'll be spitting out microprocessors on your desktop, and that's just silly. I mean, there's no reason to do it that way, and it would be more expensive than doing it using conventional techniques. On the other hand, printing does have certain key advantages. One is it's inherently compatible with flex. So if you're working on flexible substrates, it has advantages. 2, if you want to cover large areas with low functional density, it has big advantages, and that's where we've already seen commercial deployment of print. So for example, some of the, I've run a research center in Korea for many years, and it turns out some of the Korean car manufacturers have now moved to print-based fabrication of the heaters for their sort of car defrosts. Those are now printed, whereas they used to do it by coating followed by subtractive. So those are some changes that have happened. And then finally, print is really good because it's an additive functional material deposition process. It's really good for combining multiple functions on the same substrate. If we were doing it subtractively, we would put down a layer, pattern it, put down another layer, pattern it, put down a third layer, pattern it. Here, I just go in with 3 different layers, and I can put them in different locations without a problem. So provided I can meet the performance requirements, printing is pretty attractive. And that has driven where printing is having success and where it has failed. When people first talked about print, they were perhaps overhyping what it could do. But the reality is where print has had success is in applications which are characterized by those. Large area, flexible, low functional density. Fortunately, those are all areas of tremendous growth right now. So that's been good as far as where we are going. Now, the interesting thing about print, as I mentioned earlier, is the industry that's working in printed electronics, and practitioners such as myself who are working in printed electronics have perhaps been rather naive because we don't have that entire knowledge flow that exists. I'm saying microelectronics, but really I'm more generally talking about subtractive patterning-based processing. So if you look at microelectronics, you can learn a lot for how we in printed electronics should approach this. So let's say I buy a tool from you. So I buy a PVD tool, or I buy a stepper, or something along those lines. When I buy that tool, not only do I get the tool, but there's a material set that goes with it, and I get a guaranteed process of record when I get that tool. And that means if I'm a circuit designer, or for that matter, even if I'm an integration person, I don't need to know all the details about this tool. And that allows me to sort of advance knowledge very quickly. In print, that's not true. If you look at what we do, we synthesize our own materials. We build our own tools. So what's holding the industry back, in some ways, is that lack of knowledge flow. Coming from the other end, the average circuit designer, and I consider myself at least part-time a circuit designer, the average circuit designer really doesn't know much about materials. And so what does the circuit designer count on? Well, the designer counts on really good device models that describe how the devices work, which allows him or her to design a circuit without knowing the interior of the circuit. And then from that circuit, we produce a layout which will ultimately go onto a mask. To make that happen, we have design rules. And what those design rules do is they provide physical descriptors of how the manufacturing processes work. What are the line widths you can achieve? How far apart do your features need to be to get what you want, so on and so forth. And then you put those together, and that allows you to start producing features. But here's where we have a big problem in print. And this is an area where my group focuses, so I'm going to spend a little more time on this. Let's say in conventional lithography, I'm trying to project a dog leg such as this. If that is the feature that I put on my mask, and I'm working on the limits of my resolution, what I get doesn't look that much like a dog leg, because the refractive effects as the light scatters through the mask and scatters in the resist mean that there's feature encroachment, and what happens is what should have been a dog leg ends up being rounded. I've got rounded corners, my features have pulled back. Not so good. So what happens in a real mask? Well, the layout person lays it out as a dog leg, but there's software, EDA software, electronic design automation software, that sits between the layout person and what actually gets put on the mask that calculates, well, you want a dog leg. I won't project a dog leg. On your mask, I'm going to put something like this. It has serifs and carets and mouse bits, such that once the light goes through that feature, what I finally get looks much more like the actual dog leg that you want. It's called optical proximity correction, really well understood. Commercial, don't have to worry about it. It just gets done. How? Because we've got really good physical understanding of sort of the diffractive effects in lithography, and we can therefore encapsulate all of this knowledge in code. That is missing in printed electronics, and we are really naive about it in that we're always pushing the limits of resolution, But we say, oh, I want to print a dog leg, I'm going to try to print a dog leg. One of the lessons that I try to bring within my group anyway is don't try to print a dog leg. Print what you need to print such that once it finally dries, it gives you a dog leg. And the physics is different. It's not optical proximity correction or light scattering. The physics is fluid mechanics. So in one of those remarkable things, my students, who are electrical engineers largely, some material scientists, spend a lot of their time thinking about fluid mechanics. And that has changed how we approach print. And we put it all together, and then we can start building complex systems. So we've published a lot on how we do this. We know how to create smooth lines. We know the fluid mechanics of droplet drawing. We know how to create corners. We know how to create crosses. Our goal ultimately is to give out free software that will allow people to use this without thinking about it. We're not quite there. Certain features we know how to do really well. Other features we don't fully understand. But I'm going to show you one vignette of some of the things that we do. So it turns out a fundamental structure that we always want is something like this. A source and drain line separated by a narrow gap. Two lines, fine lines, minimum resolution, separated by a narrow gap. That turns out to be a really difficult structure to print well. And the reason is that there's a fundamental consequence of how droplets dry that causes the ink to flow to one end of the line. In fact, it's the part of the line that you first put the drop down as the droplet dries. We understand the physics completely. We know exactly why that happens. But it results in a really big problem. You end up getting these bulges at the end of the line, and those bulges mean you get a neck at that point. And that's really, if you're a transistor person, that's really bad, because that's a high field point. It's going to degrade your transistors. They will almost certainly fail there. So what do? Well, we've got software that essentially says, oh, you want to print that? Don't print that. Print this. Print two hockey sticks. And what these do is it turns out these sort of manage the pressures during drying and cause the ink to pull away from the corners and give us much better line width and line space control. So these are the kinds of things that we do. And in lithography, or in coding for that matter, you take an understanding of this for granted. But in print, we're still sort of learning. And that's what's made this an interest. As an academic, it's made it an interesting field for me. We've been able to learn a lot. On the other hand, as an industry, it does mean that this has been a real struggle to sort of push through this. But the second piece I'm going to talk about, and I'll spend a couple of more minutes on this because I think this is relevant for you. Even if you don't do print, there are probably many applications for, if you're, let's say, a PVD person, there's probably many applications where you tried to justify the use of PVD, but adoption was limited not by PVD. I mean, sputtering has gotten really cheap, right? I mean, it's really hard to compete with the cost of industrial sputtering. But you were limited by the cost of the associated patterning. So it's not your fault, but you still got held back because people didn't know how to pattern what you were putting down. Well, I'm going to argue that print, combined with what you do, can actually enable that. In other words, you may still be putting down a thin film, and I may no longer be putting down a functional material. I may be putting down an etch mask, but I will allow you to pattern much more cheaply in large areas. So, but to get there, what we need to do is we need to take printing and make it competitive with large area lithography while delivering the cost of print. So one way to look at that is to do this sort of universal plot of goodness for printing, which is resolution over here on the x-axis and throughput on the y-axis. And unfortunately, as in most processes in our world, there's always a trade-off. The things that give really high resolution tend to be expensive. The things that are really fast tend to give really low resolution. What we set out to do was we said, well, let's take a technique, gravure. We picked gravure for various reasons, and see if we can take a low-resolution technique and make higher resolution while maintaining the same throughput. I will admit right away that there's probably other ways to approach this. You could take one of these techniques that are high resolution and make them faster, but we decided to attack it this way. And we've had a lot of success. It's certainly not the only way to get here. So to understand this, and I promise I won't show, I don't think I'm going to show any equations, but I'll at least show you graphically how we've got this under control. So first, let me explain briefly what gravure printing is. So in gravure printing, what you have is you have a hard metal cylinder, typically stainless steel coated with chrome or copper coated with chrome, and you ink it with an ink. Now the ink has to go in and fill the cells that are etched into the cylinder. So the first process that matters then is filling. Once the ink has filled the cells, it's everywhere. So you have to wipe the excess ink off, and that is done using a doctor blade that sort of scrapes the ink from the regions you don't want it and ideally leaves the cells completely filled, and we call that wiping. Then that substrate, that roll comes down and touches down on the substrate we are trying to print on, and ideally most or all of that ink would transfer. In practice, it's on the order of about 50%. Most of the ink would transfer, and so we have a process called transfer. And then finally, that ink that has transferred spreads, dries, and forms its final shape. Now, we've spent a lot of time publishing on this. I'm not going to talk about this too much today, but I will spend some time talking about these today, just to sort of show you how this process works. So we'll begin by talking about filling. So what happens in filling is you have this ink that is dispensed onto this roll, and the ink front is spreading to cover the roll. And ideally, it's filling the features that you've etched into that roll. So we built this printer, and I mean, we still use it, it's instrumented like crazy. It has high-speed cameras everywhere, lots of measurement capability everywhere, just so that we could understand the physics of gravure. And so here's a series of snapshots out of one of those cameras, and you can see an ink front approaching an isolated cell. So that's a cell that's etched into our cylinder, and the ink front is approaching it. And it approaches it, and we notice something interesting. When it reaches that corner, it actually pins right at that corner. And then if you use a high-speed camera and zoom in and see what happens, what you actually find is it fills the cylinder through a capillary filling process. So it moves along the contact wedges, it moves along the corner to fill the cylinder. Now, what is it doing, therefore? It is going in to fill the cylinder, and it's pushing the air out. But let's say I go too fast. Let's say I'm printing or filling too fast. What happens is the top, in other words, this front over the top, covers the cylinder before I have expelled the air. And that turns out to be something we've observed. We've actually observed it experimentally. There's something called air entrapment that happens, and you get a bubble inside the cylinder. That's bad, because now I didn't fill the cylinder as much as I wanted. My cylinder is maybe only 10% full instead of 100% full. So that's a really big problem. So I now get to give you my first process rule. And my first process rule is filling works better when you go slow. If you go fast, you're probably going to trap air. Okay? Let's look at wiping. Now, in the wiping process, and for those of you who are going to watch this online, I believe this video will not work in your online version, but at least for those of you in the room, you can see this. So what I'm going to show you now is I'm going to show you the wiping process, where what we have is we have a doctor blade that is trying to clean up that cylinder. And what it's trying to do is it's trying to leave the cells perfectly filled, but it's trying to clean everywhere else. But watch what happens. So I'm going to show you a doctor blade over here, and there's a series of cells passing by. And as each cell passes by, you notice something that is very non-ideal. You notice that behind every cell, there's a little tail that gets left behind it. And we call that, for obvious reasons, drag out. We're not very imaginative when we come up with names for our processes. So what happens in drag out is kind of interesting. It turns out that as the doctor blade passes each cell, ink wets the back of the doctor blade and rides up. And then once it passes the doctor blade, it's in a non-equilibrium condition, and a substantial fraction of that ink gets redeposited back down again behind each cell. So what that means is two bad things have happened. First, while I was passing the cell, I sucked ink out of the cell. So my cell, which was 100% full, is now less than 100% full. And second, it deposited in a region that I expected it to be clean. So this is bad. So I now get to give you my second process rule. My second process rule, because it is a wetting-based process, in one of those weird things that happens in the world very rarely, wiping actually works better when you go fast, because it doesn't wet as much. Unfortunately, life is a little more complicated than that. If you go too fast, there's so much pressure that builds up in the fluid that it'll actually deflect the doctor blade up. There's huge amounts of pressure. Our blades are made of stainless steel, and they still get deflected up, and then you deposit this sort of uniform lubrication film. It turns out it models really well by lubrication theory. a lubrication film gets deposited behind it. So I'm going to modify my second process rule. My second process rule is wiping works better when you go fast, but not too fast. And transfer is also sort of interesting. It turns out experimentally it's really difficult for us to measure transfer in line. We can measure it after the fact. But it's been really well modeled theoretically, and it turns out experimental results sort of back this up. I won't go through the details, but it turns out transfer also works better when you go fast. And the reason is that the transfer process, the fraction of transfer depends on how, there's this bridge that forms between the two, and the amount of ink that gets deposited versus held back in the cells depends on how quickly those lines move on the substrate. So if you go fast, it gives them less time to move, and so you can transfer more ink. So you put it all together, and you get this plot of sort of how to print well. And it turns out we get a universal behavior. And we'll just focus on the red line for now. If you go really slow, so our y-axis is goodness. We want to be as high up on that curve as we can. That would indicate we're printing what we want to print. When you go really slow, you don't print very well, and the reason is your wiping is dragging ink out of the cells. If you go faster still, you're also not printing really well, because now you're trapping air inside the cells. If you go really fast, you think things are good, but there's also a residue that gets deposited where you don't want it. So there's a region that is perfect, or as good as it's going to get anyway, and that turns out to be right over here. And it turns out it's universal. We've tested it for hundreds of inks on hundreds of substrates at hundreds of print speeds and viscosities, and we always get that curve, and that universal point is always the same. So that now gives us a design rule when we are trying to scale gravure from tens of microns to single micron or submicron. All we do is we design our processes to hit that point. Capillary number is sort of, it's related to various things, but it's the major parameters that affect this are ink viscosity and printing speed. So here's sort of an example of how that works. Now, these are larger features. I'm going to show you state of the art in a minute. But let's say I'm trying to print my source and drain structures, which are these two lines that are separated by a really narrow gap. Well, if I go too slow, my lines are completely bridged, because the drag-out process pulled ink from the first line and covered the second. If I go too fast, I don't get much pattern because I've trapped air inside the cells. If I go just right, I can do really good lines. Now, what does really good mean? This is what really good means. These are about 1 micron lines, actually 1.5 micron lines. You can see the line edge roughness is really good. Printed at 1 meter per second. These are conductive, printed on large area plastic substrates at 1 meter per second, and we can do this. And there's no reason to stop here. This is just a tooling limitation right now. I absolutely believe we can go further. So gravure can scale at least to 1 micron while maintaining those high print speeds. That's really exciting. Now, this is printing of conductors. But for you, you could imagine printing resist at high speeds and then patterning your thin films. So if you ever hit an application where someone says, well, your sputtering is cheap, but I have no way to pattern, you've got a way to say, hey, you ought to consider print-based patterning. It'll still give you the high quality of your sputtered films or your evaporated films, but now it gives you patterning that is much more scalable. So we use that then to print devices. And so here's the first device that I'm going to show you. So this is a printed transistors. We print gates, print a gate dielectric. So print source drain, print semiconductor, print gate dielectric, print the gate. All printed using, every layer is gravure printed, so printed at 1 meter per second. And if you look at what our transistors will look like, they work really well. I mean, they're printed on plastic. They run at low voltages. They give switching characteristics that are on par, in fact, better than amorphous silicon transistors. And today, we have these running at over 10 megahertz. On plastic, printed at 1 meter per second. So we really can produce some pretty decent devices this way. Now, these are organic transistors, so they're printed using polymer materials for the dielectrics and semiconductors and nanoparticles for the electrodes. But it turns out we've moved far beyond that. In particular, in my group, we focused a lot on printable inorganics. And the main reason is really performance. It turns out organics sort of hit an upper limit at a mobility of about 1 to 5 centimeters squared per volt second. With inorganics, we're running at several tens of centimeters squared per volt second. So the particular inorganic that my group has had a lot of success with is tin oxide. Now, tin oxide is, many of you are very familiar with tin oxide. Tin oxide is an interesting material for us for a couple of reasons. It's a semiconductor. It's got a relatively high carrier concentration, so you have to manage that. But it is transparent, has relatively high mobility, And we know how to formulate really good inks out of it. So we formulate these sol gel inks that turn out to be very printable. And then when we print transistors out of them, we get these really transparent transistors. So there's an array of transistors on this sheet of glass that is sitting on top of this substrate. And you can see how clear it is. It's about transparency on par with ITO-coated glass. So it really is very good. And the way we build these transistors is we use tin oxide as our semiconductor. We use zirconia as our dielectric. And the performance is really good. Mobilities of 40 centimeters square per volt second. The temperatures that we need to process these are about 400 degrees Celsius. So we are doing these not on plastic, we're doing these on glass, but we also do it on flexible glass. So we've printed these on Corning's Willow glass without a problem. And the transistors work really well. Now, it turns out these were spin-coated transistors. Printing of sol gels is sort of tricky. And printing of sol gels is tricky because there's an effect that some of you are probably aware of called the coffee ring effect, which as droplets dry causes them to form ridges. And sol gels are really problematic with respect to coffee ring because as they dry, the sol gel gels and it sort of freezes that ridge into the form, and so it's really hard to get uniform thin films. So we've had to do a lot of tricks to get this to work. And in particular, we use a technique which we call a fugitive wettability switch, which is, well, it's nothing particularly fancy. What we do is it turns out to prevent the coffee ring, one of the things you want to do is maximize contact angle hysteresis, which is the difference between the advancing and receding contact angles. One way to do that is to have nanoscale roughness on your substrate. But if we're printing on glass, we don't really have easy ways to induce roughness dynamically. So what we do is we put down, by print, a very thin layer of an organic, and then we hit it with UV ozone inline. And that micro-roughens the organic. And then when we print the sol gel, it forms a nice smooth shape. When we convert the sol gel afterwards at 400 C, it turns out the organic burns off and doesn't seem to impact performance. So take a glass substrate, print our gate. So we put down this thin organic, print our gate, print a gate dielectric, convert it. During that conversion process, it drives off the organic. Then we do it again, print our source drain, print our semiconductor, convert it. And we're able to make really nice transistors this way. You can see none of those coffee rings. They look nice dome-shaped profiles, and the transistors work really well. All of this work has been done using inkjet. We have not yet published our work using gravure. We've published work on gravure-printed conductors using TCOs on Willow glass, but the transistor work has not yet been published, but it's coming. Now, I told you that I'm a transistor person, but I do want to show you some of the other things that printing enables. And in particular, since printing allows me to put different materials in different locations in a very material efficient way, I do want to show you some of the other kinds of devices that we can build. And in particular, I'm going to show you MEMS, printed MEMS, microelectromechanical systems, because this is something that we've had a lot of success with, and we can get really good devices. Now, fundamentally, the reason we started doing this is back when I was spending most of my time working on organics. Our printed metals are pretty good. Our printed conductors on plastic in thin film form will give us conductivities about 70 to 80% of bulk. So that's pretty good for a printed film. But our semiconductors were never very good, right? I mean, our organic semiconductors had mobilities of 1. Silicon is sitting at, or thin film silicon is sitting at mobilities of 3 to 400, at least in terms of Hall mobility, about 100 in terms of field effect mobility. So we're about 2 orders of magnitude worse. So that got me thinking, well, let's try to make switches that don't need semiconductors. Let's use switches that uses the materials that we know how to do well, which is metals. And so that's how we got started on doing metallic MEMS. And we specifically build structures that look like this. So we build these cantilevers, and it turns out we're able to print these. So these are fundamentally 3-dimensional structures, but we're able to print them. And these cantilevers are electrostatically actuated. So we have a gate here, and when we apply a voltage on the gate, it pulls the cantilever down to bring it in contact with the other electrode. And then when we let it go, it pulls away. And because it's a metal-to-metal contact, the on-state resistance is really low. It's on the order of about 3 ohms. And surprisingly, these devices switch really fast. They switch at about 1 megahertz. So if you wanted to use them for displays, they're actually pretty attractive because their on-off ratio is really good. Because they are a mechanical contact, their switching characteristics are absolutely abrupt. And if you care about displays, they're really interesting because the quality of a display depends on the off-state leakage. The blackness of black really depends on the leakage current. So we've used these to make sort of display pixels, and they work really nicely. Turns out one of the problems with our current technology is that, I apologize, this video does not seem to work on this machine, but I'll describe what you're seeing, or what you should be seeing. It turns out that as you're switching these cantilevers up and down, you actually introduce fatigue right at this corner. And then ultimately they fail. But we can get about 10 to the 6, 10 to the 7 cycles before they fail. Now, that turns out to not be good enough for a display, because if you do the math for a display, you need about 10 to the 10 to 10 to the 12 cycles. So we're not quite there for displays. But where we are having a lot of success is actually for solar and photovoltaic applications. And the reason is the following. If you look at a photovoltaic panel today, like a silicon photovoltaic panel, or even a thin film panel, it's 100 cells, 144 cells, all connected in series. And if any one of those cells is off its peak operating point because of dust or clouding or shading, the whole string goes off its peak operating point because they're all in series. Now, people know how to deal with that. If you can put a micro relay on each cell, you can do dynamic switching of series parallel connections to make sure your entire string is sitting at its peak operating point. Yet nobody does it in practice because it's too expensive, because you have to hand wire them. Well, it turns out these devices have the current carrying capability to do this, because 3 ohm on contact resistance, we get about 100 milliamps per contact. We can build arrays of contacts without a problem. And they have enough good enough switching characteristics for these applications. So where we are having success is printing these directly on thin film photovoltaics to do that dynamic switching. And the devices work really well. But again, I want to show you how we build these devices. So I showed you earlier that what we need is this suspended cantilever. Well, that's really hard to do. As you probably know, one of the problems is as you're going through your processing, if there's any drying process, the stiction from the drying forces will cause this cantilever to pull and get stuck down. That's a big problem. I mean, the traditional MEMS industry deals with this a lot. So what we want is a relatively stiff cantilever. But it turns out the switching voltage also depends on the stiffness of the cantilever. So we want something that's very well controlled. And it turns out we've sort of found an interesting way to do it. So I told you earlier that the coffee ring effect causes these ridges, which are bad for normal devices. But we really like the ridges here because it allows us to make a U-shaped beam for free. So here, again, using the knowledge of fluid mechanics that we've developed, we actually print structures and we pick conditions that print such that we intentionally get ridges. And in a single pass print, we can produce these ridges that then give us a U-shaped beam. This is an example of something that would be really hard to do using conventional techniques. It's really hard to get a structure that looks like this in one deposition process. But we can get it for free by exploiting the characteristics of fluid mechanics, in other words, how droplets dry. And this then allows us to make these cantilevers that are stiff enough to hold their configuration and then switch at exactly the right voltage. And we've extended this technology a long way right now. So these are what the transistors look like today. These are 3-terminal devices. Turns out 3-terminal is not good enough. You need 4-terminal. I'll tell you why in a minute. They switch at between 1 and 10 microsecond switching speed. On resistance is about 3 ohms. So you can see we get a 3 ohm on resistance. And they switch really well. Turns out a 3-terminal device is not sufficient. And the reason is a 3-terminal device means that if your conductive terminal floats because you got it connected to something else that's charging up, your switch that was in contact can pull out of contact. So what you really need is a 4-terminal device. But we've been able to do that. Essentially, what we do is we print a T-shaped structure. And when we pull our cantilever down, it's making a bridge between 2 additional terminals. So that gives us 4 independent terminals, therefore a gate, a body, a source, and a drain. And it looks remarkably complex, but our yields are really high. We're able to make these mainly because we've learned how to make those ridges in a very controllable way. And then the nice thing is once you have a body terminal, you can make CMOS. Because depending on how we bias it, we can make it behave like an N-type device or a P-type device. We can dynamically change the voltage at which it switches. So we're actually able to start making functional, fairly complicated logic systems right now. And this is kind of where we focus a lot of our work these days. Now, I've been showing you only switches to this point. The next frontier that we're going for after with these is actually in sensing. Many years ago, it turns out this field has sort of slowed down. Many years ago, people showed that if you took conventional MEMS cantilevers
and you functionalize the ends of them with receptors, because the switching behavior of the cantilevers depends on the mass, if you put a chemical receptor on the end of a cantilever, the switching behavior depends on whether that receptor has detected what it's going to detect or not. And people showed parts per trillion level sensitivity out of those. Never really took off. One of the reasons was to make it work well, you need arrays of these systems. Well, we can build arrays really easily, and we can put different receptors on each array really easily because we're printing. And so the next thing we're going after is actually trying to use these for sensors. And so hopefully if I see you again in a year or two, I'll be able to tell you about that. But these 4-terminal devices also work really well. As I told you earlier, they switch 10 to the 5 cycles. We really need to try to get for sensors or solar, this is fine. I'd really like to go after logic applications, which means I need to get these up to about 10 to the 10. I'm not sure how to do that. Fatigue is something we're still struggling with. We're working on it, and we'll see how it goes. So I've tried to give you a snapshot here of where printed electronics is. And to put it in a succinct way, we've really pushed the limits of resolution today. We really do understand the physics of print. And that's allowed us to produce high pattern fidelity structures. Now, unfortunately, and this is sort of a real pity, there's maybe 3 groups in the world that really think about print in this way, really treat printing as a science. But if you do, it turns out you really can push the limits of what you can do. But it does require you to think about print in a way that's sort of beyond how graphic arts thinks about it. Because we put fundamental understanding in how we design our tools. We put fundamental understanding in how we synthesize our materials. A lot of work on ink formulation, and then tying it to processes to ultimately build devices. And then by coupling this entire range of knowledge, what we're able to do is produce highly functional systems at high throughput on flexible substrates at low cost. And really, the key point is we treat printing as a science. And if we do, we can really push the limits of what we did. So I'll end right there. Obviously, the luxury of being a professor is I didn't do any of this work, right? It was done by my students. And I've been really lucky to have a fantastic group of students and postdocs over the years. And they've been fantastic, and some of them are in industry, some of them have moved on to academia. And we've had tremendous support from various funding sources over the years, National Science Foundation, Merck is EMD Chemical in the US. They did a lot of the organic work with us. BASF did a lot of the inorganic work with us, and then some government and associated funding agencies. So I'll stop right there. I thank you for your time.